So welcome to the fourth TA session on this course on design and analysis of algorithms. No student has joined so far. Let me start the session anyways. I'll connect my iPad and then share the screen. Are you Anand? Anand, am I audible? Okay, so I hope my screen is visible, and if there are any issues, then let me know. Okay, so this is week 4 of the TA sessions on DAA. It's 11th. Yeah, so from now on, we will be looking at algorithms on graphs. Okay? And the first very simple algorithm would be, first of all, what a graph is. That you have a collection of nodes, which are, or you call them as vertices. And these vertices are connected by edges, right? And each edge connects two nodes in a graph. Let's say U and V, and this edge can be either directed or undirected. Now, before I go to graphs and discuss algorithms and problems on graphs, let's discuss a simple problem. Let's say I have a linked list. It's a simple problem, but a nice one. So the question is as follows. I'm given a linked list of size 2n. So it's an even sized linked list. And what we want is, so it's an even sized linked list. The goal is to reverse the second half of the list, right? So there are 2n elements in the list. It's single, like you have, so every node will have an pointer to the next node. Okay, so it's not a doubly linked list, it's a single linked list of size 2n. And the goal is to reverse the second half of the list. So elements from n plus 1 to 2n you want to reverse. So goal is to reverse the second half of the list. And we have constraints that the running time must be order n, and I'm not allowed to use space other than some constant size space. So second half of the list in time order n, and extra space that I'm allowed to use is a constant space. So you can use some variables, but the number of variables must be constant. And space order 1. So that's the problem. Okay, I'm given a linked list. It's a singly linked list, not a doubly linked list. A singly linked list of size 2n. That means it's an even size linked list, and the 6, 8, 10 like that. And the goal is to reverse the second half of the list. Okay, we want to reverse the second half of the list. So second half meaning elements from n plus 1 to 2n. That is what I meant by second half. And we want to do it in order n time. Okay. And the space must be order 1. So let's take a simple example. Let's say I have my list as let's say the list has size 10. I'm just denoting the elements by A, B, C, D, and E. And then the remaining 5 elements I'm going to denote by red color. Okay? That's the second half of the list. So we do not know the size of the list in advance. It will come as an input to our program. Okay. So that's like one input instance. And as an output, I would want so first half must remain the same. There should be no change over here. And then the second half must change. So what I mean is you must reverse the second half. So exactly the changes are as follows. Right, so see, here J was the last element in the list. So if I want to reverse the second half of the list, I must have J as the first element in the list, followed by I, then H, then G, and F. So that is what I want as the output. J, I, H, G, and F. Is the problem statement clear? Did Anant say something? Because I was not able to, I could not hear you. The other student, Shri, can you please unmute yourself and say something? Because I just want to make sure that there is nothing wrong from my side, because I'm not able to hear anyone. Like it is Anant, I saw him mute and then unmute. Yeah, I'm still not able to hear.
Ma'am, it is clear. The problem statement is clear.
Oh, okay, okay. Yeah, I was not able to hear you. I could see that you are unmuting yourself, but I was not able to hear you. Okay, so how do we go about solving this? We will just see this problem, and once we have the solution, then I'll move on to graphs, and we will see some of the problems which are not covered in the course. We'll see there are some very interesting problems on graphs based on DFS that we will see in the next 2 lectures. Today I'm going to explain to you the graph, basics of graph, the search algorithms, how the numbers in those search algorithms can help us solve some non-trivial problems on graph. But before that, I wanted to discuss this problem. So see, the first thing is here, the key thing is that the list has size 2n. Okay. So, and we want to reverse the second half of the list. So our first target should be to identify the midpoint of the list. So can you think of how do we identify the midpoint of the list?
Um, we can use some kind of a counter to
Okay.
count the number of links, to count the number of next pointers up to n,
Okay.
and then from there on, we need to reverse the next pointers of the subsequent elements.
Okay. So count like going to the middle of the list, you're saying that we will keep track of it via some counter variable. So that is one way of doing it, right? So what you can do is once you have the input, you can find the length of the list. So for instance, here it is 10, and then you can have a pointer which you will run from 1 to 5, and it will end up at exactly the middle element in the list, the nth element in the list. Okay, that is one way. And since we also want, we want to reverse this entire second half of the list, the other and the more elegant way would be, let's say I want to have two pointers, one pointing to the middle of the list and the other pointing to the end of the list. Because ultimately what we want is when I reach the end of the list, I would want that E must point to J. So I want to avoid multiple passes. Instead, in a single pass over the list, I want to have two pointers such that one points to the middle of the list, the second points to the end of the list. And we can do this without even first, computing the length of the list. So can you think of one way of doing this? The key here is that the length is 2n. So I want to initialize two pointers, take two pointers. I don't know how to initialize them, but at the end of my, when I run those pointers, I want one pointer point to E and another pointer point to J. Let me call those pointers as mid and end. Can you quickly think of how to achieve this goal first?
Ma'am, the end pointer will definitely point to the null. So we will,
No, we want it to point to the last element of the list. Let's say J is the last element. I want end pointer to point to J and the mid pointer point to the nth element of the list. Okay, so here is the answer, simple. So initially I'll have my mid point to A. Okay, so I'll have mid pointing to A and end pointing to the second element in the list. So this is my initialization. Now can you think of how to advance these pointers so that after n iterations, mid is exactly pointing to the middle element, the nth element, and end is pointing to the last element of the list. Once we initialize the pointers like this, I want to run a loop n number of times. And after the loop ends, I want mid point to the nth element and end point to the 2nth element in the list.
Will increment mid by 1 and end
Yes,
by 2 times.
exactly. Right. So mid, we will advance to mid dot next, and end we will advance to end ka next ka next. Okay, so we'll advance end by 2 steps and mid by 1 step in each iteration. And that will ensure that after n iteration, middle is pointing to the mid element, the nth element, and end will be pointing to the 2nth element. So I hope this part is clear to the other student as well. Okay, so once we have this, now the goal is, now we want to do the second task, right? We want to reverse the second half of the list. So usually if, let's say the problem was you were given a list and you wanted to reverse the entire list, how would you do that? How many extra pointers do you need to reverse a list?
At least 2 pointers would be needed.
Yeah, we need at least two, but just with just 2 pointers, we'll not be able to reverse the list, because see what happens is, say I have 2 pointers. Let's say I want to reverse uh, this link, okay, from F to G. I want to make it from G to F. So I'll have one pointer pointing to this, one pointer pointing to, let's say P and Q. Then I reverse this pointer, but then I will lose the information that the next element from G was H, right? So the moment I reverse the pointer from G to F, I will lose this information. So I need 3 pointers actually. So here is how we go about this. Let me name those pointers as P, Q, and R. How do we get the... 1 second. So let's say I have a pointer P. This will be used to denote some, like, so let's say I have a pointer Q, which is used to denote the current node. Right? So we want to reverse the next of the current node, and I will reverse the next of the current node to the previous node. So P denotes the previous node. And so that I don't lose that information that I just discussed, I will have a pointer to the node which is next to the current node, right? So R is current ka next, so next node. So initially I'll have P set to null. Just copy this figure. Okay, so Q is the current node, so that's the current node. P is initially null, and R is the next of the current node. So that's my R. Okay. So what are we going to do now? So P is, at this point, P is null. What should we do? See, even if I change the pointer here, right? See, this F was the first element in my second half of the list. What I ultimately want is that the next of F must be null, because we want F to become the last element in this list. So F's next must be the previous element, right? Which is currently equal to null. So we'll set the next of F equal to null, which means I'll just run this statement. Q next equal to P, whatever is the previous node. Currently it is null, fine. So F's next will be set to null. And then what do? Now note that we are not really losing on this information, right? So we already have a pointer R, which is pointing to the previous next element of F. Right? So if I just had these two pointers, I would have lost the access to the next of F, the previous next of F. Okay, so that is why I need this extra pointer R. So can I now advance my pointer?
Yes, ma'am.
Yeah,
I think.
right. So now this F is pointing to null. And so we will now advance the pointers, and I'll just now rewrite over this. So this is now the previous node, and this becomes the current node, P and Q. Okay. So what we do is previous node is equal to the current node. The current node is equal to the next node. Now we will repeat this, right? Where do we set the pointer R? So as long as my current node is not null, while Q is not null, I'll first find the next of, I'll set the next of Q in R, right? I'll store that value and then update, then make the necessary updates. So then the main update is done in this statement, which is actually doing the job of reversing the links. And these are to, go to the next element. This is to save the previous next element of the current next. So in the second iteration, we see that the current node is not null. So we first save its next node in the pointer R. Right? So R points to H. And then Q's next equal to P. So we will set G's next equal to F. Okay. And finally, Q is equal to P is equal to Q and Q equal to R. So this becomes P, this becomes Q. Okay. Again, since Q is not null, I'll set this to be equal to R. I mean, this is the next pointer. And again, Q's next equal to P. So this points to G. And this becomes the previous node. This becomes the current node. Final iteration, again, since current is not null, I'll have this set to R and then reverse the pointer. Right? So I will point to H, and then this becomes P, that becomes Q. Okay, there is one more iteration. In the next iteration, still I see that Q is not null. So now R becomes null. because the current node is the last node in my list. And then we will set Q's next equal to P. So J points to I, and this becomes P and this becomes Q. So finally, when we go and check this condition, Q becomes equal to null, we exit from the loop, and the entire list has been reversed. Okay, so we do have J pointing to I the way we wanted it. J pointing to I, then I to H, H to G, G to F, F to null. And what else do we want? One
The
update. Huh?
Yeah, the midpoints next should point to the current to the to
To
P
the
here.
end node.
Yeah.
Yeah. You can set it, I mean, both P and end, both are pointing to the same node. So we'll just make mid, after exiting from this loop, we'll set the next of mid equal to end. So any doubt on this? I don't see the,
Mm,
okay. There
no,
is some delay. Right? Sorry.
it is clear.
Okay. So let's now move on to graphs. What is a graph? Have you all gone through week 3 lectures? Or at least some of the week 3 lectures?
Yes, ma'am. Up to DFS I have gone through it.
Okay. So let's see this, let's recap this BFS and DFS because we are going to use them extensively to study our, some other problems on graph. So let me draw a graph here. So I have 8 nodes in my graph. Okay, so just in case the other student has not gone through uh, the lectures, a graph is you have a collection of nodes. Okay, so each of this is a node. We can label them. Let's say A, B, C, D, E, F, G, and H. And then between any two nodes, we will have edges. Okay, so some nodes will be connected by edges, some not. Okay, so if every pair is connected, it's a complete graph. And otherwise, it's not a complete graph. So here is an example of a graph that is not complete. Then every edge can, the edges can either be undirected or directed. So here, all the edges are undirected. This is an undirected graph. So one, such, uh, it's a very general model to represent a problem statement, right? So for instance, later in the course, you will see shortest path problems, right? Where every node might be representing a city, and these edges will carry some weights as well, which could be the time taken to travel from city B to city C, or it could be some, it could be representing something, some other parameter, maybe the cost of traveling from B to C, right? So these could represent, the flight. There is a flight from B to C. I'm looking at the cheapest flight from B to C, and that might be the fare. The weight of the edge might be the fare associated with that flight. So in some sense, this the weights will capture the cost of that edge. So in a shortest path problem, I will be, I might be interested in going from a city A, let's say, to another city, let's say F, and there can be multiple paths to go from A to F, and we are interested in the path which has the smallest cost, right? So if the graph is weighted, where every edge has a weight, then the length of the path will not matter. Length meaning the number of edges in the path won't matter. What really matters is the total weight of all the edges in that path. Whereas if it's an unweighted graph, then it actually is the length that matters. I'm interested in the shortest path. That means I'm interested in a path that has the smallest number of edges connecting A to F. Okay, so those are the very common problems that we see with graphs. Now, one of the basic problem in graph is you have a node and you want to search for that node. Okay, let's say I have this graph and I want to search for a node F. So in that case, there are two algorithms which are uh, the breadth first search, BFS in short, or breadth first traversal, and the other is depth first search. These are the two algorithms which are used to search for a node in a graph, right? And the problem, if I change it slightly, let's say I don't want to search for a node in a graph, but I rather want to traverse the entire graph. That means I want to visit every vertex in the graph or every node in the graph. Both we will use the same algorithm. It's just that if I'm using a traversal algorithm to search for a node, I will just uh, stop whenever I encounter the node I'm looking for. Right? So we will see the traversal algorithm using the breadth first search and depth first search. Okay? So traversal meaning I want to visit. It's not that I'm interested in one particular node, but I want to visit every node in the graph. Okay. So how does BFS work? Breadth first search. Both BFS and DFS, you will start with a node, and then you want to start exploring the other nodes in the graph in a particular order. So how does BFS work?
In BFS, we traverse the nodes level wise. So, like the nearest neighbors, we will explore.
Mm-hmm.
We will explore, given a particular node, we will explore the nearest neighbors.
Ah, so adjacent neighbors, and then we repeat, right?
Yes, and then we repeat.
Right. So to maintain that, so suppose I start with some node. Let's say I start with A here, and I see its immediate neighbors are B and D, or the adjacent nodes are B and D, I will next visit B and D in a particular order. So that will be usually given in the problem statement. If you have a node U and it has multiple neighbors, so they have some labels. So usually we would want to visit them in the dictionary order. So here A has neighbors B and D. I would like to visit B first and then D. Similarly, if I were to start with E, then we see that E has neighbors D, B, and F. So in what order I'm going to visit D, B, and F? If it is a dictionary ordering, then I'll visit B first, followed by D, and finally I'll visit F. So in what order we visit the nodes of the current node, the adjacent nodes of the current node, that will be given in the problem statement. For our discussion, we will assume that we are going to visit these nodes in the dictionary ordering. Okay, if they are numbers from the smallest to largest number. Okay, so let's say we start with A. Right? So that is the first node we are going to visit. I visit A. And then I see that A has neighbors B and D. So what we do is we visit B first, okay, and then we go and visit D. Okay. Now, you know, uh, in a graph, if I pick a node, it can have multiple neighbors. So I need to store those neighbors somewhere, because in the next iteration, again, I have to repeat. So whether I want to repeat from B or D, or at least to keep track of all the nodes which are not yet fully explored, I need a data structure for that. So here I'm going to maintain a queue data structure. Queue data structure. Let's say I'm denoting it with Q. So initially Q had A inside it. Then I visit A. So I'm going to delete A from the queue and then insert B and D in the queue. Okay, so in the next iteration, B and D are there in the queue. So next, so every time, whatever, as long as my queue is not empty, because you see this graph is coming as an input to the algorithm, right? So it's not, the algorithm is not looking at the whole graph upfront. It's looking at the graph node by node. So we start with the first node, put it in the queue, then we explore it in the sense that we will visit its adjacent vertices, B and D. And once we have visited B and D, we are done with A. So we'll remove it from the queue. Okay, so in the next step, I'm going to insert its adjacent nodes into the queue and then repeat, right? Repeat as long as the queue is not empty. So we'll keep repeating. And also, okay, I'll come to that later. So now in the next iteration, I'm going to explore B. So I visited B. And I see that its neighbors are D, E, G, F, and C, right? But some of the neighbors might have already been visited. So we are not going to revisit them, okay? So you will see why not revisit, what will happen if we revisit. So essentially, we want a tree out of this breadth first search, right? So if I revisit a node, I'm going to get a cycle in the tree. I mean, which does not make any sense, because tree has to be an acyclic graph. So there won't be any, we won't be revisiting a node. So when I come to B, I see that B is sitting at the front of the queue. I now want to start exploring B. I'll see its adjacent nodes and visit all the unvisited nodes, right? So I'm going to visit these nodes. I'm going to visit E, F, C, and G. And in a particular order, let's say in the dictionary order, although D is also a neighbor of B, but D is already in the queue, so it has been marked as visited. So from B, I'm first going to visit C. Then I'm going to visit E. Next F. And in the last step, G. So all these nodes which I go and visit, I'll place them in the queue and remove B. Okay. So now D comes to the front, and these nodes that I just visited, I will insert them in the queue. C, E, F, and G. Okay. Next, I come to D, the node D, which is sitting at the front. And I see that D has neighbors A, B, and E, but all of them are already visited. So we are just going to remove D from the queue and mark it as completely explored. So D has been removed. Now what remains is C, E, F, and G. Okay. So come to C, the node C. C has neighbors B and F. Both of them have already been visited. Do nothing, remove it from the queue. So I'm just going to mark it here. We remove C. Next, we come to E and see that E has three neighbors, D, B, and F. All have been visited. So we don't do anything, just remove it from the queue. Next, coming to F. So F has multiple neighbors, 1, 2, 3, 4, and 5. 4 of them have been visited. The only node that is not yet visited is H. So we will visit H from F. So we'll remove F and insert H into the queue. In the next step, we see that G is sitting at the front. All the neighbors of G have been visited. Do nothing, just remove it from the queue. Next is H. All the neighbors of H are also visited. So we just remove it from the queue, and then we see that our queue is empty. So the algorithm terminates. Okay. So that's how the breadth first search will work, and it will essentially give us a tree. Right? So if let me draw this as a tree. I started with A. Then from A, I first visited the node B. And next I had visited D. From B, I had visited C, E, F, and G. Okay. And from F, I visited H. So that is the BFS tree we had obtained. Okay, so this is my BFS tree for this graph. So is the BFS tree going to be unique, or it can be different for a given graph? Can I?
If we interchange the order of B and D, then it will be a different.
Different BFS tree. In fact, if we change our start node, it's going to be an entirely different BFS tree. So it's not like one-to-one correspondence between the given graph and the collection of different BFS trees you can have with a graph, right? You can have, I mean, in fact, if there are n nodes, you can have at least n different BFS trees to begin with, right? Where the root node itself will be the different. Okay. Now, this is a tree, right? How do we define a tree? A tree is also like a graph. You have nodes and edges, right? Just that the edges have a special name. These are tree edges now. I mean, they don't have a special name. They are tree edges. But how do we define a tree?
Trees cannot have cycles in them.
Yeah, that is one property. And the other property is, there are two properties that define a tree. No cycle. Right? So tree has no cycle, must be acyclic. And the other thing is it must be connected. No cycle and connected. Okay. So the moment we say that it does not have a cycle and it is connected, if my tree has n nodes, how many edges it will have? Exactly. How many edges will be there?
It will be n minus 1.
Why n minus 1?
I must, because all of the nodes are connected to each other.
Yeah. Can you give us very simple explanation that why exactly n minus 1?
For every two nodes, we need one edge to connect. So it is one less than the number of nodes.
That does not uh, explain that a tree will have n minus 1 edges. For instance, I say that, okay, here are, let's say I have 4 nodes, and I'm saying that for every pair, I have one edge connecting them. It can have multiple, the number of edges can be more than n minus 1 that way, right? The explanation, I mean, I know that you know it, but the explanation is not correct. The point is, uh, so how many root node? I mean, a tree will have exactly one root node, right? So barring that node, there are n minus 1 nodes. And each of these non-root node will have a parent, a unique parent. That explains why the tree must have exactly n minus 1 edges, right?
Yes, ma'am.
Yeah. Okay. Now, in a BFS tree, you have, so since it is a tree, it's going to have exactly n minus 1 edges. And in case my BFS, in case my input graph was a directed graph, these edges would have been directed edges. Okay, so I'm considering undirected graph here. And if the graph itself was not connected in the sense that there was, say, let's say I also have a couple of other nodes. And let's say the edges are like that. This is I, J, and K. And let's say there was no edge from any of the nodes in this component to any node in this component, then I will have, if I do a BFS on such a graph, the resulting data structure, right, after executing BFS will not be a tree, it will be a collection of trees, which is called as a forest, right? So how do you ensure that all the nodes in my graph are visited in BFS? If let's say the graph is not connected, how do we ensure that? Let's say I start my BFS from A, right? So it's only going to visit those nodes to which it is connected. I mean, to those nodes which are connected to A. So I will not be able to visit I, J, or K. So how do I then visit I, J, or K? So what you do is, whenever you want to implement BFS, just make sure that, I mean, because the input graph can be disconnected, you must have an extra loop outside your, BFS function, which will ensure that no node remains unvisited. So initially, what you do is you will mark each node as unvisited, right? So there will be some array, let's say visited, and for every node you will set it to be equal to 0. So in your main body, whenever you see that this, even after performing the BFS starting from A or any other vertex, if you see that BFS for a particular node, I mean, a particular node has visited is still equal to 0, then I will start BFS from that node. Okay. So for instance, I see that, okay, BFS of J is equal to 0. In that case, oh sorry, visited J is equal to 0. That means J is still unvisited. I'll start another BFS call from J. Okay, so that is going to visit J first. First I'll visit J. Then from J I will visit I and K. So first I'm going to visit I, and then I'm going to visit K. So I and K will be in the queue. Next we'll remove I, then remove K. Queue becomes empty, and this part also gets completely explored. So whenever the graph is disconnected, I'm going to have a BFS forest and not a tree. Okay. Now, this, let's say I just have one tree in my BFS forest. Okay, forget about the second tree. Let's say I just have one tree in my forest. So these edges were used to uh, traverse the entire, all the nodes in the graph, right? So, and these we are calling as the tree edges, BFS tree edges. Now, there are certain edges in the graph which do not, these are not the tree edges, right? But they were present in the original graph. So the question is, I'm going to call these edges as the non-tree edges. Once you have this BFS tree, these non-tree edges can be present between what all nodes. So since it is a BFS tree, first of all, I'm going to assign the levels. So the root node is at level 0. Then B and D, they are at level 1. These nodes are at level 2 and level 3. And so 3 is the height of my tree. This tree has height 3. Level 0, level 1, level 2, and level 3. So question is, can I have a non-tree edge between two nodes at the same level? Is it possible to have a non-tree edge between two nodes at the same level?
And here it is visible, but I do not know the reason. Like between B and D, both are at the
Yeah,
same level.
B and D are at the same level, and in the graph, original graph, we do see an edge between them. Okay. Similarly, is there any? So let me mark other edges, C and F. Then D and E. That's a different edge. F and G. And G and H. Okay. So there are, in fact, in this original graph, there are 3 non-tree edges which are, connecting two nodes at the same level, B and D, F and G, C and F. So we can have such edges. The reason is, it's not going to, see, how do we do the BFS? We started from vertex A. I mean, here in this example, we started from vertex A. We saw that A has two neighbors, B and D. We don't really care about whether B and D are connected or not. So we will first visit B, and later on we will visit D. Okay, so it's complete. There is nothing stopping me to have an edge between B and D. Clear?
Yes, ma'am.
Yeah. And we can also have edges. Let me mark the other edges as well. So for instance, I have an edge between D and E. This is also a non-tree edge. Then between E and F was also there. So between G and H, also we have a non-tree edge. Yeah, that is it, I guess. Yeah. So we have these non-tree edges as well, right? So D and E, this non-tree edge connects a node in level 1 to a node in level 2. And between G and H, again, a node in level 2 with a node in level 3. So we can have such edges as well. Do you see that is also not going to cause any problem?
Yes.
Yeah,
Yeah.
because when we come to B, we visit E, okay? And later when we want to explore E, we see that E has multiple neighbors. E has a neighbor D as well, but D was visited via A. D's parent was A. So that is also fine. It's not going to change my BFS tree. Now, so far what we have is the properties of BFS tree and the non-tree edges associated with a BFS tree is, one, we can have non-tree edges between nodes at the same level. Second, we can also have non-tree edges between nodes at the adjacent levels. Okay, so for instance, level I and level I plus 1, I can have non-tree edges. Now the question is, can we have, let's say, a non-tree edge between a node at level 1 and a node at level 3? Can I have something like that in the original graph? Is such an edge possible? Yes or no?
I don't think it would be possible because we would have visited H immediately after D.
Exactly, right? So yeah, if there were such an edge, then H would have come at level 2 and not at level 3. Okay, so we cannot have such an edge in the graph. Once I have the BFS tree, the only non-tree edges that we can have go from, connect nodes at the same level, or they connect nodes at the adjacent level. Okay. So it's 5. We will take a 10-minute break here, and then we will see DFS and study its interesting properties. What all non-tree edges can be there in a DFS tree, and then we will see some interesting problems which uses those properties to solve the problem. So we'll break for 10 minutes. I'll resume at 5:10. So let's continue our discussion on graph traversal algorithms. Next, we will see the other way of traversing the graph. So here one approach could have been that you start with A, then go to B, then from B go to E to F, F to G, G to H to F, but F is already visited, and then backtrack and backtrack to H to G, right? And then to B, from B I could have gone to E. Right? So that is another way of traversing the graph, which is known as the depth first search, DFS in short. By the way, this BFS, when you run BFS on an undirected graph, and let's say my problem was that I want to find the shortest path from a node to every other node. Let's say from A to every other node in the graph. Can I use can I use BFS to solve that problem?
Uh, yes, ma'am, because BFS gives the shortest distance between two nodes in
Yeah,
terms of number of edges.
right. Because it in terms of the number of edges, right? So in case my graph is unweighted, where the edges do not carry any weights, BFS indeed solves the shortest path problem for us. It will, wherever the source node or the node where we start from where we start the BFS, it will give us a tree. And essentially, if all the nodes at level 1, they are at a distance of they are at a distance 1 from the starting node. All the nodes at level 2, they are at distance 2 from the starting node, and so on and so forth. And you cannot have a shorter path from, let's say, from A to C. Okay? There cannot be a path of length 1 from A to C. Again, because of this reason that there cannot be non-tree edges between two nodes which are at non-adjacent levels or not at the same level. Okay. Anant, you are an undergrad student?
Yes, ma'am, actually, I'm in third year.
Third year, BTech?
Yes,
Where?
electrical engineering
Which institute?
from NIT Silchar, Assam.
Okay. 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 So DFS, let me again draw an example first, and then we will discuss the main properties of the DFS tree. Um, So I'll be extending this example later. So that is, I'm not using the numbers starting from A. Let's say these nodes are G, H, I, J, K, and L. I'm taking a small example here. And later, for another problem, we will extend this graph. So I'll add on the nodes like A, B, C till F later. Okay. So the edges are as follows. Now for DFS, let's consider like a directed graph, because we are going to differentiate between certain non-tree edges and the directions will matter. Right? You can run a DFS on an undirected graph as well, but directions, if we have a directed graph, then the non-tree edges, there can be multiple classifications of non-tree edges, and in general, like there are two different non-tree edges, and you can only distinguish between them if you have directions on the edges. So just for that reason, I'm going to take a directed graph here. So I'm just thinking in what direction should I take this edge so that we have different non-tree edges. It's not going to work the way I have labeled the vertices. Okay, let me just give it this direction. This will not. Okay, maybe I'll extend this example a little by a node or two so that we can get the third type of edge as well, non-tree edge. Just for our understanding, for now, let's take this example itself. So we are given this directed graph, and we want to traverse every vertex in this in the depth first manner. Okay. And when we are doing this depth first search, so of course we would want where to start with, like the starting vertex. Can be any of the node in this vertex, in this graph. And we want to maintain some numerical information, right? So you must have seen those lectures where Professor Madhavan is maintaining the pre and post numbers with every vertex. So I'm going to call them as start and finish. So when do I start exploring a node, and when am I finished exploring that node? Okay, so I'm going to assign start and finish numbers with every node in this graph as we execute the depth first traversal. Okay, starting with 0. Um, so we'll have to maintain a counter as a global counter variable to assign these start and finishing number for every node. So let's say that we start our traversal with J. So since we are starting with J, I'm going to assign it a start number 0. Okay. And whenever, so of course, again, from starting from J, I can only go to nodes which are adjacent to J. So we have outgoing edges from J to, in this example, I have outgoing edges to G and L. And whenever I have a choice, I'm going to pick the one which comes earlier in the dictionary order. Okay, so we will always choose the one that comes early in the dictionary order. Okay. So from J, I'm going to visit L, sorry, G. Okay. So we go and visit G, and G I'm starting at time 1. From G, I have just one outgoing edge to an unvisited node. So I'm going to visit that node. Okay. That's I. I start it at 2. Okay. So we started with J at time 0. Then at time 1, I reach G. And at time 2, I reach I. Okay. Now I see that I has only one outgoing edge, and that node has already been visited. Okay. So if I draw it like a tree, so far it will be like this. I started with J. From J, I went down to G, G to I, and then I see an edge from I to J. Okay, but we see that J has already been visited, right? So the times so far are, I visited J at 0, G at 1, and I at time 2. Now there is only one edge which goes back to a node which has already been visited. There is no other edge going out from I, so we are done exploring I. So at that time, I'm going to assign it a finished number. Okay, so for every node, I'm going to maintain a start and finish numbers. I'll be denoting them with S and F. Okay. Now, when I'm done with a node, when I have already assigned it a finishing number, I'm going to backtrack. Right? I'll go to the node, its parent node. So I'm going back to G. Now from G, I see that if there is an unvisited node, I'll visit it. But there is no outgoing edge from G which goes to an unvisited node. There was only one outgoing edge. So we are done with G as well. And at time 4, we finish exploring G. Then we backtrack, go back to its parent, right? So we are back to J. So J still has an outgoing edge, which goes to a node which is not yet visited. So I'm going to visit, so I'm still not done with J, right? So I'm going to visit L from J. And at what time I am visiting L? What is the starting time of L?
It should be 5.
5, right? So I visit L at time 5. And from L, I see there is one edge going, one outgoing edge, right, to an unvisited node. So we are going to visit that node, which is K. From L, I go to K at time 6. Then from K, again, I go and visit H. I'm visiting H at time 7. From H, I see that there are two outgoing edges, one to G and one to L, but both of them have already been visited. Right? So let me draw the tree here. From J, I went to L. From L, I'm going to visit K. From K, I visit H. And from H, I see two edges, one going back to L. And there is another edge that goes from H to G. But these are not these red and blue edges. These are not tree edges. Only these black edges are the tree edges. Okay? And the timings are we visit L at time 5, visit K at time 6, and visit H at time 7. And since from H I cannot go anywhere, I'm done with H, right? So I'll assign a finish number of 8 to H. Then I come back to K, its parent, and we see that from K also we cannot start exploring another node. So we have finished with K at time 9. Similarly with L at time 10, and then I come back to J, and there are no more outgoing unexplored edges from J. We assign it a finishing number of 11. Okay? So 0 gets 11, J gets 11, 5 and 10, 6 and 9, 7 and 8. Now, view these start and finish numbers associated with a node as an interval. Okay, so J has, for instance, J starts at 0 and ended at 11. Okay, so that is the whole interval associated with J. Just giving you an example. So if I look at G started at 1 and finished at 4. Starting at 1, finishing at 4, that's the interval associated with G. Right? So you view these start and finish number as an interval associated with that node. When does it start? When do we start exploring that node? And when do we finish? When are we done exploring that node? The finish time. Now, once you have, completely, once the DFS is fully executed, we are going to get this DFS tree. You see, these black edges form the tree. Now, the remaining edges are the non-tree edges here. What all different kind of non-tree edges can we have? So one set of non-tree edges could be like this, right? Going from a node back to a node which has already been visited. So when you come to I and see, okay, I'm starting I at time 2, and I'm just exploring the edges which are going out from I, but we see that, oh, it has only one outgoing edge. It's going to a node which has already been visited. It means that this edge will go from the node I to some of its ancestor. Okay, so this node is going to connect a node to its ancestor. It could be its parent as well. So parent or ancestor. Such an edge is called a back edge. This edge is called a back edge. Similarly, here when I come to edge, I see that there are two outgoing edges. One edge is going back to its ancestor, one of its ancestor. Okay? So this is a back edge. And there was another edge which was going from H to G, but H and G do not have a ancestor-descendant relationship. What do we call such an edges? Are these covered in the lectures? The classification of non-tree edges?
Ma'am, I think it is covered, but actually I did not cover. I did
You
not
have
go.
not.
Yeah.
Okay, okay, okay. So such edges, non-tree edges, which do not, I mean, if you look at the vertices of these non-tree edges, because they do not have a ancestor-descendant relationship, these edges are called as cross edges. Okay, so we have back edges, we have cross edges, and we can also have, other type of, one more type of edge, which is called as the forward edge. And this will be again an edge from a node to one of its descendant. It's like the reverse of the back edge. For instance, I could have an edge from J to K. Although in that case, the tree structure would have been different. Such edge can also be there, non-tree edge, and these edges we call as forward edge. So we can have back edges like this, going from a node to one of its ancestor, a forward edge which goes from a node to one of its descendant, and cross edges where we don't have the ancestor-descendant relationship. Is the classification of edges clear? These are the only three types of edges I can have in a DFS tree.
And ma'am, this is applicable only for directed graph, or can we have this for undirected as well?
For undirected as well, we can have, but in that case, the forward and the back edges will be the same.
Okay.
Yeah. And can we have cross edges there? If I have an undirected graph, can I have a cross edge? So come to G. Can we have cross edges in an undirected graph? I don't think we can have cross edges, right? So for instance, if there was an undirected edge between G and H, I'd have gone from G to I, then I would have explored H as well. So in case my tree is undirected, I will probably only have one type of this non-tree edges.
Okay, ma'am.
But in case of directed graph, we can have these non-tree edges can be classified. The non-tree edges can be either back edges or can be like forward edge. Or it could be a cross edge. So now my question is, if I have a back edge in my DFS tree from a node U to V, let's say I have a back edge from node U going back to V, how are their start and finish times connected, related to each other?
Ma'am, start time will for the uh, for u will be greater than v because we are visiting it later.
Yeah, so start time of u will be, no,
And it
we, okay, so we are going from u back to v. So what did you say? The start time of u will be larger, right?
yes, yes. And the
Yes, so
finish will also be uh, lesser.
finish of u will be smaller than that of v, correct?
Yes.
Yeah. So yeah, because if I take my DFS tree and some path in the DFS tree, let's say u uh, is an ancestor, v is a descendant. I mean, u is an ancestor of v. Then I can have a back edge from v to u, going back from v to u. And of course, since I'm traversing in this order, I started exploring u first. So u's start time must be, uh, oops, this should be v, and I have back from u to v, right? So the start time of v must be before u, right? And uh, I cannot finish v before I finish u. So the finish time of u has to be before the finish time of v. And this just gets reversed if we had a forward edge. So let's say I have a forward edge from u to v. In that case, which interval will be contained? Whose interval will be contained in the other? If I have a forward edge from u to v, let's say
V's
the
V's
v z.
interval. Yeah.
Yeah. So if that's the interval for u, the start and finish time, v's must be fully contained inside that of u. Okay. So the simple observation is like that. If I have a DFS, for instance, this is a DFS tree. Look at the interval for J, right? It spans 0 to 11. Then G is 1 to 4. So it is contained in this interval. I is 2 to 3. It's contained in the interval for G. So it is like that. So any path in the DFS tree, if you take from the start to one of the leaf nodes, the intervals always follow this containment order. Okay? Longest interval corresponding to the first node in that path, then it will contain the interval corresponding to the second node that will further contain the interval corresponding to the third node, and so on and so forth. So there is this nesting relationship in the amongst these intervals in a path, right? So with that, you can easily identify, you can easily answer this question that if I have a back edge or a forward edge, how are the intervals corresponding to u and v are related? Now, what about a cross edge? So cross edge is like you have some path in the tree. Okay, so you are done exploring that part of the tree, and now you are in some other path in the tree. You come to a node and you see that there is an edge going from this node to some node in the other path in the tree. So since, first of all, this edge is connecting a node in two different paths in the tree, there is no ancestor descendant relationship between these nodes. Right? So these are what we are calling as cross edges. Now, what can we say about the relationship? How are their intervals related? So let's say I have a cross edge from u to v. What can we say about the how are their intervals related? So it is like this, right? So let's say R is the root of my DFS tree. So there is this path. And then I'm done exploring all the nodes in this path. Right? So I will backtrack, right? Come back to R at some point. Then I will start exploring some other node in this other path, right? And then come back, come to a node. From this node, I'm seeing an edge, which is not going back to one of its ancestor. Rather, it is going to some node in the other path. It's going to some other node. So question is, how are the intervals associated with these two nodes connected? So let's say this is my node U and this is my node V.
No idea about this.
Uh, see, when I say that this path is already explored, does it mean that this node we have already assigned the start and finish number to this node?
Yes, ma'am. That
Yes,
is, yeah.
and that is true, right? So we have already assigned the start and finish to this node. Now later on, I come across this new path, right? I'm exploring this new path, the nodes in this new path. And at some point I come to a node, let me call that as node U. And we see that U has an edge going to V, which was there in the previous path. That has already been explored. So of course, the starting time of this node has to be larger than the finishing time of this node. Is that correct?
Yes, ma'am.
Right?
Yeah.
So let's say I'm just using U and V again here, but that shouldn't be an issue. So let's say U and V or U prime and V prime. So my first claim is that the starting time of U, the starting time of U prime must be larger than the finishing time of V. So that is U, and somewhere before we were already done exploring V, right? So now it's easy to complete, right? So V's start time will be, of course, smaller than the finish time. So it starts here. And U's finish time will be larger than its start time. So the point here is the intervals corresponding to V and U will be like this. They will be completely disjoint. And also the interval for V will precede the interval for U. We only start U after we had finished V. And there will be some gap. It can be small, large, depends how many nodes are there in this, how many nodes we had already visited before U prime.
And ma'am, there will not be a specific relation regarding finish time of U prime, right? Like I cannot say anything about
No, no. Yeah, it just has to be larger than the start time of U prime. It can be any number.
yeah.
So all we can say here is that we had already explored V. So its interval is going to be completely disjoint from the interval of U. And this has to come before the interval the interval corresponding to U. So the point is that if you if you take any two nodes in this DFS tree, if they are connected via tree edges, then we have this containment relation, right? So if I have a tree edge between node U and V, then V's interval is contained in the interval for U. If there is a back edge or a forward if there is a back edge from U to V, then again, U's interval is contained in the interval for V. If there is a forward edge from U to V, V's interval is contained in the interval for U. And if there is a cross edge, then the intervals will not overlap at all. So we cannot have a case where two nodes are connected by an edge and their intervals overlap. Either they will be fully contained, right? Or they will be completely disjoint. Clear?
Yes, ma'am, clear.
Okay. Now, one question. See, I had this graph, right? And clearly this graph is cyclic. There is this cycle in this graph. Also, there is this larger cycle in the graph. Now, suppose I give you a graph and I want you to answer whether this graph is cyclic or not based on using DFS. Can you use the information about non-tree edges to answer whether the graph is cyclic or not? Is the question clear?
Yes, ma'am, the question is clear. Yeah.
Just think of these non-tree edges. How will you use this information to answer whether the given graph is cyclic or not?
Something related to the duration, like the total duration.
Uh, okay.
Like the
Just
start times of I cannot find any relation. No, that is not right.
maybe try to answer in terms of the presence of these edges. See, when you do DFS on directed graph, of course, you will have tree edges. You can have zero or more back edges, zero or more forward edges, zero or more cross edges, right? These you can identify based on their starting and finishing time. So when you actually you should do this exercise, implement DFS, and for every edge in the original graph, you should be classifying it as either a tree edge or back edge, forward edge, or cross edge. Right? So you can easily implement it based on the discussions we had. Okay. Now, it's possible, right, that my graph, when I run DFS, I don't get any back edge. I don't get any forward edge, or maybe one or two. And it's possible I get zero or more cross edges. So based on the number of these non-tree edges you get, uh, which non-tree edge will guarantee that the graph is cyclic?
Forward and backward can back edge can guarantee.
Okay, so cross edge does not, right? Because cross edge, I'm going from root node. So here I'm only seeing edges in this direction. and then an edge going in this direction. So clearly this is not guaranteeing any cycle. Even forward edge will not help, because a forward edge is something like, okay, I go from root node to some node, and then when I come back to a node, I see that there is another node, another for outgoing edge, but it's going to a node which has already been visited, right? So that is also not going to guarantee a cycle, because all the edges are pointing in the forward direction. The tree edge is also pointing in the forward direction. The forward edge, as the name suggests, is pointing in the forward direction. That is also not guaranteeing any cycle. The only way to get a cycle is via the presence of a back edge. So clearly here, you see J to G, G to I back to J, and it already gives me a cycle, which, I mean, the cycle has 3 nodes in this.
Okay,
Clear?
yes. I need to find all the all the
Yeah,
non-tree edges first. Then
non-tree edges. So basically, when you implement this, try to classify every edge when you explore the I mean, when you do this, implement this DFS, right? So every time you will be exploring an edge, you need to classify this as a tree edge or a back edge or whatever edge it is. And if the problem was just about answering whether the graph is a cyclic graph or not, then the moment you find one back edge in the graph, you can safely, stop and say that the graph is cyclic. Clear?
yes, ma'am. Clear.
Yeah. So this DFS, a cyclic graph, is equivalent to saying that the graph has a back edge. There exists a back edge. And what about the case of BFS? Let's say I had an undirected graph to begin with, and I have the same question. I want to identify whether this graph is cyclic based on BFS. How do I check that?
So here, if any non-tree edge is present, then definitely there will be a cycle.
Clear, clear. Correct, right? So any non-tree edge, presence of any non-tree edge guarantees that G is cyclic. Okay, maybe I'll not start the discussion on the problem that we'll be covering in the next lecture anyways. So that will use the properties of DFS and these non-tree edges we had discussed. I'll ask some other problems as well based on the, this part we need to understand really well, that how do these connect, and some more advanced problems. And once we have understood that, then we will move on to other problems on directed graphs, right? So my plan is that next 2 lectures we'll be looking at problems which are not covered in the lectures, but I would suggest that you finish all the lectures for this week so that you have a better understanding, especially that topological sorting. That is also covered in this week, the topological sorting.
And that is in week 4, I guess. This was covered in week 3.
So week
Yeah,
3
no, sorry, week 3 only it is covered, topological sorting. Yeah.
topological sorting, right? So so basically, if topological sorting means if your graph is acyclic, then you can have an ordering on the nodes in the graph such that when you order them, all the edges will be in the forward direction. Right? A simple example could be like this. Let's say I have A, B, C, and D. I want to have an example of an acyclic graph. So there should not be any cycle. My smallest example could be just this. with A, B, and C. Even with D, it's fine. I can have more edges. And the question is, I want to sort the nodes in this graph in a particular order. So what I mean by sorting here is, or it's also called as linear order, I want to have an ordering where if I have nodes, let's say, okay, the ordering here is simple, A, B, C, and D. If I put all the edges from the graph in this order, so A to B, then A to C, B to C, C to D, B to D, you see that all the edges are directed in this forward direction. Okay. And if there was a cycle, then you will not be able to do this, right? For instance, if A, B, and C form a cycle, you cannot do a linear ordering of this. And if there is no cycle, you should always be able to find a linear ordering, wherein when you put the edges in the graph, they will all be pointing in the forward direction. So topological sorting is an algorithm to find a linear ordering of the vertices so that all the edges point in the forward direction. Okay.
Okay.
Yeah. So, I mean, in the lectures, it's covered in detail, and the professor will also give you the algorithm. There are a couple of ways of finding this linear order. But yeah, finish all the lectures, and we will have a class on Friday. That day, I'll discuss a new problem. Okay.
Okay.
Okay. So, any questions?
No questions from my side.
Okay. So, thank you for attending.
Yeah,
We'll
thank you.
Yeah, we'll have a class on Friday, same timing.
Okay, sure.
Thank you.
Thank you.